Swayam Prabha. Digital India. Educated India.
So, for that you need log n space. Just a small caveat, the space is also now a random variable, because you have to store what? The value of x, right. So, the number of bits that you need to encode capital X would also be a random variable, and that is your space. So, your space is also now becoming a random variable. Like say for example, time was a random variable in your case for quick sort or quick select. Fine. Now for the analysis. Before I get into this analysis, notice this fact that one instance of Morris algorithm is returning to you a value of x, right. How can I apply this idea in here? So, I can run multiple independent runs of Morris and then add their outputs, right, and then divide by n or rather t, whatever the number of instances I run. What that will do for me? That will keep the expectation same, but it will reduce the, and that would tell me that my output is close to the expectation, because Chebyshev would then work nicely, right. So, I can do this. Now, see how a probabilistic idea translates into an algorithmic idea. What you just now do is run independent copies of the same algorithm. The stream is the same, but what you are doing is you are running independent copies of the same algorithm. So, each independent copy has this probability inbuilt to it, right. So, the outcome is a random variable and they are IIDs. So, then you can as your final answer return the average of them. That would help, right. So, I will come back to this idea a bit later. Now, we will prove this, and now you understand why I had this correction factor of -1, because I want e to the power of 2 to the xn minus 1 equals to n, right. So, you understand why that correction factor is there, because what do I want at the end? I want this e to the expectation of this n hat to be n. So, that means expectation of 2 to the x minus 1 should be equals to n. So, that is why I have that 1, right. That is the reason I had that correction factor. I will use this notion of conditional expectation. Why do I need it? Because remember, my increments were probabilistic. I incremented x as x plus 1 with a probability of 2 to the power of minus 1. It was not that I incremented it always. I incremented it based on its current value. Right? So, that means the more you go towards the end, the probability is getting down and you are adding less and less. How are you compensating for that? By raising it to the 2 to the power of. Okay. Base case is where n equals to 0, x n equals to 0 by the initialization step. I told you that I would use this initialization step for the base case of my induction. So your x n is equals to 0 and e to the power of 2 x n is equals to n plus 1. x0 is 0, so 2 to the 0 is 1, expectation of 1 is 1, n is 0, so it satisfies, right. So, base case done. Now, for the induction step, I look at 2 to the x n plus 1, the n plus 1th step. I see it in terms of the previous things by conditioning. Okay with this one? This is just the definition that I did. Just remember this. It is just this one. Probability of y into expectation of x conditioned on y. As I said, you sum over all possible values of j. I am summing over everything. Why is it so? think over exercise. You incremented x with a probability of 1 by 2 to the x, right. So, that is why this is 2 to the j plus 1, and you did it with a probability of, right, and it is the next one is the case where you did not. So, your value remained 2 to the j, that was with a probability of 1 minus 1 by 2 to the j, right. Now, this is an expression, just simplify it. If you simplify it, you will get something like this. This is nothing but 2 to the xn, and this is just the sum of the distribution. So, this should be 1. It is just the sum of the probabilities taken over all possible values of j. So, that should sum to 1, and this is by the induction hypothesis. What is e to the 2 to the power of xn? That is n plus 1, right. That is my induction hypothesis. So, that is what I set out to prove. E to the 2 to the power of x sub n plus 1 should be equals to n plus 1 plus 1. So, that is the reason we had this correction factor of minus 1. So, now this is an unbiased estimator. So, Morris algorithm has been able to figure out an unbiased estimator for what I set out to count. So, whatever you are returning is also now an unbiased estimator, because its expectation is precisely the quantity that I want to count. Now, let us see with this unbiased estimator how am I going to get, rather than how Chebyshev is going to behave, because if Chebyshev behaves well, then that means my unbiased estimator is concentrated around the expectation and I am doing good. Query still now? Yes, you have questions. Yeah, j can be anything, you know, I have no bound on it, right, what I am counting. So, I look at all possible values of j. For some of them the probability might be 0, whatever it is, right. So, I am looking at the full domain of this estimator. good meaning low error probability. Okay. So, what I want is this n hat minus n greater than epsilon n to be some delta, and Chebyshev would tell you this to be 1 by, mind you, this epsilon is the error we discussed in the morning, right? Epsilon is the error parameter. So, expectation of n hat minus n whole square. Now, if you just plug in these values of n hat, you would get to something like check this, I may be wrong, maybe plus minus 1 here and there, but the main thing in here to notice is the dominant term is this 2 to the power of 2xn, right. So, I need to control that. So, there are some tedious calculations, we need really to get into them. 2 to the xn, and you can show, which I will not get into, that expectation of 2 to the xn, this would be equals to 3 by 2 n square plus 3 by 2 n plus 1. You can prove this just in this fashion, right. So, the way you proved expectation of 2 to the xn equals to n plus 1, you can prove that this is like this. So, I will not prove it because it would be tedious in here. Take this as an exercise, and it is like similar to the earlier claim. Now, I will need this. See, what was my goal? My goal was to control the variance of the estimator that turned out to be unbiased. So, I need basically the variance of this quantity. And in that I will use this claim. This was my output, right. Again, if you go through, so write this as expectation of this minus expectation of this whole square, go through a few steps, use the previous claim, and you can show that this is upper bounded by n square by 2. Again, I am not getting into these calculations. So, these calculations would, as you understand, there is a square term. So, in between you would somewhere need this 2 to the power of 2xn, and I have already found that out. So, plug in those values, get through these calculations. These are just calculations, nothing else, because all the ingredients are there. So, one can prove that this variance is upper bounded by n square by 2. So, if that be the case, see, mind you, for Chebyshev an upper bound on the variance works, right, because I want what, a probability to be less than variance by something, whatever is in there was in here, square of that, right. That was the form of Chebyshev, something minus something greater than epsilon, that was upper bounded by variance by this error. So, if I can have an upper bound on variance, say for example, I have not been able to estimate the variance exactly, but an upper bound also works, right, because the inequality is in this direction. So, I have already got a variance upper bound on the estimator, it is n square by 2. So, what does Chebyshev give me? Gives me So, what I did was, I did two things. Once the algorithm was done, I showed that the output that I gave was an unbiased estimator by proving the expectation. Then I did some messy calculations with the variance to show an upper bound, plugged it into the Chebyshev's inequality to come up with this. Now, is this something good? See, obviously, epsilon should be a small quantity between 0 and 1, right. So, if you look into this 1 by 2 epsilon square, when is it 1? When epsilon is, so figure out the value of epsilon for which this probability is getting close to 1. Something like that. So, for most of the values of epsilon, you are getting a probability value which is almost telling you nothing. So, that means this Morris algorithm, though it gives me an unbiased estimator, but in terms of tail inequality, in terms of the concentration result, is very poor. Now, what do I do? I take recourse to this idea. I run independent copies of Morris IIDs. So, the estimator would be the same, it would be an unbiased estimator, but what I would get as output is a reduced variance. Fine. What would this reduced variance do for me? It would push down the error probability bound of Chebyshev's, right. So, now I can improve Morris by running some multiple copies of the same algorithm. So, let me call this to be Morris plus. As we will see, maybe not today but tomorrow, that would also not give us a very good tail inequality bound. So, then what I would do is, so this is now going to be fun. So, I have these instances of Morris, right. I club some of them and take their averages. So, I have some Morris plus instances. Now, what I will do is, I will take the median of those values and show by an application of Chernoff that would give you a good tail inequality. And that is actually this trick of reducing the error probability by allowing more space proportional to. So, what I will do is, I will make the space proportional to this epsilon and delta in some way, right. So, space would get to log of 1 by delta increment, and I will have an epsilon factor there as well. So, at the cost of some more space, we can push down the error probability. One, you are by now sure that this IID random variables, this theory helps us in pushing down the variance. But this trick of taking medians over Morris plus, so the structure of the algorithm is now as follows. So, I will do this messy calculations tomorrow, but I will just try to give you this idea. So, what happens is, so these are all instances of Morris. So, all these individual dots are parallel runs of Morris. I club some of them. How many do I club? That would actually depend on the error that I want out of the tail inequality. Those things we will fix tomorrow. So, we club them and then take their averages, because each one, the output given by each Morris is a random variable and they are now all IIDs. Okay. So, now what I do is take average. When you take average, this is now Morris plus. So, now you have this Morris pluses. Now, Morris, so there are now these instances of Morris. So, say for example, you know, if there are say a many such Morris instances, you group each one say by S, then you have A by S Morris plus things, right. Now, what you do is take median of those A by A's values. And you return that as your output. So, what we would do is, in this part, see, Morris to Morris plus, the mathematical theory that is helping us is what we did at the beginning of today's class, this IID thing, sum of IID random variables. From Morris plus, so let us call this getting to the median as Morris plus plus. So, Morris plus plus will be an application of Chernoff to show you that this error probability can be made manageable. Now, what happens is this gives us a nice framework that if we can design an unbiased estimator of a problem with some constant probability, then at the cost of some more space I can turn it into an error probability that I want. See, mind you, my goal was to design an epsilon delta algorithm at the beginning, right? Remember it? Yeah. So, my goal here in this algorithm was to have this. So, in your input of the algorithm, so epsilon and delta are input parameters. So, the user will tell you what error probability the user wants. The user will tell you what approximate error the user wants. Based on that, so if the user is asking for a very tight bound in terms of a very low error probability, then the space would obviously increase. Mind you, when we did this error calculation, see this Chebyshev, look at this Chebyshev calculation. This error is 1 by 2 epsilon square. This is not dependent on delta in any way. I wanted the error probability as delta, and I cannot set this 1 by 2 epsilon square equals to delta, because delta is an input parameter, right. Remember this, that is actually, for this reason we have to do so many things. So, I repeat, the problem is a stream coming, I want to count an event. The user also gives me an epsilon, an error parameter and a probability error delta. I have to design the algorithm such that this happens, that the estimator that I give is counting from the exact value by this epsilon n, and that probability is delta. But till now I have not been able to do it. The error probability that I could give you was one by 2 epsilon square, and this may be nowhere close to delta. The user could have given anything, any damn delta, right. Now, by this trick of IIDs and Chernoff, I will bring that error probability down to delta, but at a cost of a space, right. So, that we would see tomorrow. So, if you have queries, do ask me. This was a bit heavy, no? I assure you it will get heavier. But did you get the philosophy of what is going around? Then there would be messy calculations. I mean, you have to get your hands dirty with this. Because see, most of the heuristics that you do What do? You design a heuristic, you have your benchmark, you run it. No one is asking for a guarantee, right? But if someone asks for a guarantee, you have to mathematically show it. And then you cannot escape these calculations. No way.